Hello, this is Professor Urban, about to deliver a talk about AI in ellipsometry. Let's jump in. The idea here is that we're going to use AI to solve a problem that's been frequently solved by numerical methods. And put myself in here. So we'll give a brief history about the AI stuff, and we'll talk a little bit about MATLAB and how it's being done, and then some examples on different film systems. So, and there's just too many things to put citations, so please forgive me. A little bit of a history here. Well, the idea about how does learning happen in a human or in an animal started around 1900, and by the 1940s we had sort of an idea of what is a neural network, and by the 1950s we're talking about artificial neural networks now. There were some practical applications using a perceptron learning rule, and by the 60s, though, work had suggested that it was a dead end and the theory wasn't going to allow it to work out, and so it had a downswing, and then back in the 80s upswing, because there were some ideas to get past those blockages. Also, computers had gotten a lot better, and by the 90s we had the beginning of what's I think regarded now fairly as a dramatic progress. In the 2000s we got GPUs, graphical processing units, to help in the computing side of things, and by 2024 we're getting told that the Nobel Prize winning work in physics and in chemistry were worth note for attributed to AI. So it's an important advancement. It's finally moving well. Took a long time. So why use AI? Well, it's very high speed. If done correctly, it's vastly faster, 1,000 times or more faster than least squares, and the speed is something under your control. It's simple. You don't have to have a lot of complicated decisions to make about initial estimates and things like that. And then there's no curve fitting. It just solves the problem. It could be done for curve fitting, but I'd have not chosen to do that. Just one point at a time, one wavelength at a time. And I already mentioned that we had some Nobel Prize action here to, bolster this idea is for real. So in the early days of mathematical modeling of physical systems, we had the idea of we could if we had a value of the optical properties and thickness of a film, for example, but this could be F equals ma, it could be any kind of physical or chemical system that we have mathematical models for. And the idea is we'd go from a set of numbers that we knew to another set that we didn't know by passing through a system of equations, which is, in my thinking, practically a miracle that such equations exist. They are not the physics, but they imitate it super well. And the challenge then can become, in this case, that it's easy to go from the information of the film itself and substrate to get to the measurements, but the other way is, you don't care about that so often, but you do care about having the measurements, what film made those measurements happen, and that is a difficult problem. So we want to make that work better, and we give Maxwell credit for this, although he had other people before working in electromagnetics, and the equations were basically supported empirically. So experimental work was matched up with theory. That's how we got those equations. Cool. What about in the case of learning for a human brain? Well, or an animal. So we have a possibility that there's information, and we would like to get some information out that's related to the information in. It could be throwing a baseball. You throw the ball, your eye gathers data about what its trajectory and speed and size, etc., distance, and then you're able to do some kind of a model of where it's going and put your hands in the right place and do what you got to do. So that is all courtesy of pre-processing or learning. So the human brain is able to learn by being exposed to coursework or books or lectures or personal experience. Once the learning has taken place, then the prediction is a straightforward thing. You see the ball coming, your brain has seen that before, something like it, not exact, but something like it, and then you move your arms, and you know about the mass and etc. of your arms and hands have to close at the right time. It's fantastic. It's built into the brain here from training. Well, an artificial neural network we can think of in connection with that in the same general idea of having some numbers and connecting them to a different set of numbers. But now instead of a human brain, we've got not a human brain, but an artificial neural network. So kind of an artificial brain. And that's taken decades to get developed well enough that we have some groundwork that we've able to apply. So again, there is a learning process, and the learning process is to training through a training data set. That is, known correct answers, and there's different ways. Different AI is a big tent. ANN is a part of that big tent. So we're talking about the artificial neural networks. Is trained by data. We hand it to the data, and I'll go into more detail later, but the information contained in the training data set gets transferred into the network, and then after you're done with that, and it's already trained, and that's hard, that takes a while, then the actual prediction is extremely quick, just like in catching the ball. As soon as you see the information, there's a very simple calculation that gets done here. It can be done on an edge device, some small thing that would fit in the palm of your hand and cost $25 or less. Could actually do the calculation and provide the values of the film material, so properties. So you have to train it first, though. So let's apply this to the numbers business with ellipsometry. So in ellipsometry, an optical technique, in comes an incident light beam. It reflects off of a sample. The sample can be different types. It just shows a general sample. And there's a reflection. There's also a transmission, which we could analyze, but right now we're not going to do that. And then that results in some raw data. It might be intensity as a function of angle or whatever it is that the manufacturer or the builder of the instrument has put into it to gather the data. The raw data goes through some process which is different for every instrument and commercially kind of a so-called secret sauce of how that gets done. And then out comes the measurement that we are familiar with if we want to look at the math equations, and that would either be in the Mueller matrix, a 4x4 matrix, or the psi and delta values, of which there are a total of 6, a 2x3, and you can see that there's got to be some duplication there. And here we have the sub-samples could be different ways. It could be a solid piece, it could be a film on a substrate, it could be multiple films, it could be on and on. So for those who are not familiar with the psi and delta, which is what I will choose here, is just a very brief refresher or a new view, depending on your level of experience. If light is plane polarized, reflects from a substrate, such that the S and the P component parallel and perpendicular are offset because they reflect differently, then at the peak of each of those reflected waves, which are propagating in the z direction, at the peak there will be a different amplitude at the peak. And if we look straight down the z-axis, you could see the ratio of the two intensities could be kept as an angle psi. It's a number clearly between 0 and 90. In addition, the two peak positions are going to be offset by some value delta, in general, value delta measured in degrees, where 360 degrees is one wavelength of the light. And this is all for monochromatic light, the equations. So we get the two values, psi and delta, and there's a lot of different ways to extract that from the instrument. We're working with electric and magnetic fields. Now, just as an overview, just to quickly see why this is an issue, why do we have to worry about doing the calculation? And the answer is because the equations are kind of messy. I'll show them very quickly, not go over them. The Maxwell gives us the Snell law, tells us the relationship between optical properties of the media and the incidence angle and refraction angle. We're only going to talk about, for the moment, isotropic media, parallel interfaces, and monochromatic light. There's going to be two reflections here at the 0-1 interface, and one for the P and one for the S component, and two reflections at the 1-2 interface, again for the P and the S component. So there's four values of reflection. These are complex numbers, and they depend upon the angles and the optical properties. And then once you've got those numbers, they can be put into an infinite series expansion, or infinite series expansion. And we get this, and never mind, but it counts up every single reflection all the way out to infinity. And then if we take the ratio of the P and the S components and call it rho, we can get psi and delta. So you can see right away that it's not a simple matter to go from psi and delta to the n's and the d. N is a complex number here, n minus ik. So there's three unknown numbers in principle frequently, and we've got a thickness. So it's easy to go this way, hard to go the other way. And I should get an advancement of my slide. And now we have an underlying physics issue here, which is that Maxwell, done by the Maxwell equations. And if we want to extract information, we need to have these four things to be true. In reflection, that is, at least. So we have to have a measurable reflection. Some light has to be reflected off. That's pretty obvious, right? There has to be sensitivity. That means that if the parameter of interest, let's say it's the thickness, changes, then we better have a change in psi and delta. If we don't, we're not going to be able to calculate thickness. So we need sensitivity. Obviously, every grade school student almost knows that equations have to be equal to or greater than the number of unknowns. And the condition has to be good. In other words, we're going to be looking for equations that are independent and that are result in the solution of lines that cross, not that are parallel. So we got to have those four things, or we're not getting anywhere. So now let's go to an example and bring it all together and show you the steps that are required to look at chromium film on a silicon substrate. And of all the different combinations of film substrate, if we divide it into transparent, absorbing, and semiconducting, you can see there's 9 different categories. And the absorbing films I go after first because they're limited by thickness. Why are they limited by thickness? They're limited by thickness because the light cannot penetrate very far through an absorbing material. So that makes it a little bit easier, in some ways, a little bit easier problem. And then if we go to semiconductors, which have a lower value of K and more penetration, I looked at these thicknesses and I just arbitrarily stopped at 500 for transparent. So in order to get a solution for chromium growing on the silicon or formed on silicon, it could be a growing film making a series of measurements, or it could be two different films on the same substrate. Anyway, you need the two thicknesses in order to get the number of equations and unknowns to come together. So you need, and now we're going to look at the what we need here and how to make an architecture. There's no like one architecture that's perfect or the only architecture that exists. We have to learn the architecture empirically. What I did for chromium on silicon was, of course, I'm tied down on the inputs. I have the two layers, 1 and 2, and they're two values of psi and delta. So there's 4 inputs. And there's the 4 outputs. That's why we need the 4 inputs, because there's N and K and D1 and D2. If I only made one measurement, I'd only have 2 inputs, and then I would have unknowns N, K, and D. If they were the N, K, and D, I couldn't do that mathematically. And in between are hidden layers. We'll talk about those in a moment. But these hidden layers, I happen to choose a value of 20, 2 layers, 20 each. And this, it looked messy to put all 20 here, so I didn't do that. I zoom in a little bit to give you an idea of what this structure actually does. So in a delta 2, for example, here is applied to this particular neuron. And this neuron simply propagates the value of delta 2 out to its 4, in this case, 4 neighboring hidden neurons. But each green line represents a number, a weight. So each of these hidden neurons gets a different number delivered to it. Then the hidden neuron sums the weights. So it takes the 4 inputs. So it sums the 4 inputs. And then that number, to keep it tractable, gets compressed. I like the sigmoid function. There's all sorts of compression methods. Again, empirically determined. And then this neuron, distributes its result through another weight to another neuron. And the same process goes on here, and the same process goes on here until we get out to D. So training the network means, once you've picked an architecture, training it means applying inputs and then varying the value of W until you get a result that you like. In this particular case, I used ranges of N, so of the film. So I trained from 3.2 to 3.6. These are not hard and fast. That's what I did. K through this range and D through that range. So my network would have information that would handle any film that was in that, not just chromium, any film that was in that. And I'm showing you now for one particular wavelength, and I did this for 44 wavelengths. So I did this, and these values would be different for each of the 44 wavelengths because the value of chromium, N and K, changes across that. Thickness would not change. I happen to develop a table of 1 million of values of combinations of input-output, where input and output you'll see momentarily. I happen to work at 610.8 nanometers here at a 70-degree angle of incidence, and the optical properties of silicon book values are given here. And I did 12 epochs, but that's probably too many. You'll see that in a minute. So what does the training table look like? I'll get myself out of the way. First thing that you do is make random numbers generated between the range of N, K, D1, and D2, and just put them in a table, 4 wide and 1 million long. Then you go to the first line and you say, okay, if I have a film and this is its N and K, and that's its first thickness, and that's its second thickness, what would the psi 1 delta 1 and psi 2 delta 2 be? And I use the Maxwell equations to generate that. So these numbers in the right-hand side and the left-hand side of this table agree to 10 to the 6, 13 digits of accuracy. Much more than 10 to the 6. 13 digits, the computer limitation. Cool. So that's our training set, or our training data, or our general data set. And if you pass that through over and over to the network that you saw a minute ago, and look at the error, I mean, this is too small, it comes off, I'm sorry about that, generated by MATLAB, you can see that the errors between the numbers that should be and the numbers that are predicted drops down and doesn't really drop very much. So these are epochs, meaning I go through a million, this from here to here I've gone through a million lines in the set, then I go through that million lines again, and then again and again 12 times, probably too many in this case. And here it is for the first little bit of the first epoch. So you can see that indeed at the beginning it's dropping down. That's enough to say about that. The training works. Now let's see if the training proves out to be accurate. So we take 500 numbers out of the training table, but that we didn't use for training. So the same as the training table, but different numbers. So these are unique numbers. It has never seen these numbers before. Then we pass it to the network with the weights that we've already trained, and we look at the prediction. And we look at it for 500 different values combinations of n, k, d1, and d2, and put a dot on there. If the prediction was exactly right, then the dots would all lie exactly on this line, but they don't. You can see that there is a little bit of error. Now that error is tolerable as long as it's less than the error inherent in the measurement itself. And it's also something that can be reduced with more training, a different architecture, and so on. So it's just shows you how it's done. It would be nice to know whether this produces the same size and deltas that you would expect out of that same table of 500. And so, of course, I did that and took the NK, D1, D2, passed it to Maxwell, and then calculated what it would be if it was perfect. And this is the AI prediction. And you can see that generated from what it would be from the prediction versus what it was in the table of 13 digits. And you can see a really tight, nice agreement here. So that explains already a little bit about the sensitivity, which I won't go into, but if these are tight, then that means we need a different architecture if we want more accuracy. Cool. Now that was all done at 610.8, and let's go ahead and do it at 44 wavelengths, and I don't know why I picked those particular ones, but that's what I did. And now I did another 43 networks and trained them with a million lines each, etc. You can do this nicely with a parallel computer, and not terribly long, a couple of hours maybe. And what we see here is a test basically of our neural network for a particular film. So our particular film that we're testing is represented by the black line. The black line, it could be anywhere in the range. Remember, the range went up and down quite a bit. But if right within that range, I had a film that was this of n and k, and then passed the values that I measured. Of course, I did the calculation this time, but I passed the numbers that I got for psi and delta, and then pass that to the networks, the 44 networks, then I get these red circles on the black line. Pretty darn good. And it does that all in a fraction of a second. And there's no local minima, and there's no initial estimates, and nothing. You just push a button. How about the thickness? Well, the thickness is not a function of wavelength. It should be the same at every wavelength. So I took a look at that. The two targets that I had for thickness in this case were just selected to be 12 and 15 nanometers. Actually pretty challenging, only 3 nanometers in difference. And the solution averaged 44 different solutions for thickness. and I ended up with 11.82 instead of 12. That's pretty close. And the standard deviation was 0.12. So we're looking at monolayer accuracy, and remember, it can be adjusted by changing the way the architecture looks and changing the training. And I guess I went too fast. The same thing more or less is true for the D2. It's also quite accurate. 15.02 instead of 15. All right, so we're getting the thicknesses. Well, quite frequently, that's what we mainly want. Now, we can also go back and say, well, what would the psi and delta have been if the AI predicted N and K and D1, D2 were used? And how does it compare to the number that were used in the original calculation? And you can see quite good agreement against all 44, and for both the first measurement and the second measurement. So I'm feeling a good confidence here with one angle of incidence. So what do we conclude? We have one angle. That's good enough for this level of accuracy. We have two measurements at different thicknesses are required. We can look at that all sorts of different ways. I only chose two thicknesses for this, and then we readily was able to solve or predict for the 44 wavelengths. We had submonolayer accuracy, and I said here 45 nanometers. I think I trained up to 30 nanometers. Doesn't matter. We can change that number. Now, what about another example? This example is ITO on silicon. Well, ITO is interesting material because depending on the part of its spectrum, it has a transparent region, it has an absorbing region, it has a sort of a semiconductor kind of areas as well along its spectrum. So this is a way to give everything a hard go. I will not show every single detail. It was done with a different, required a different architecture here, and it turned out that the way to get numbers that were valuable was to have inputs at different angles of incidence, 3 angles of incidence and 2 thicknesses. So we had a total of 12 psis and deltas, so we had to have 12 neurons on the input side, and we needed to have additional data on the output side. No, we did not. So we only needed 4 there, but I ended up using, I think, 80 here. Yeah, 80 in the middle. Tried different sizes. It wasn't critical. It wasn't like 85 made a difference. And we had to train it, and I went overboard. I now, in retrospect, I looked at 299 wavelengths instead of 44. All right, so I was looking carefully. I had 3 angles of incidence and 2 thicknesses. I set the ranges like before, generated the training data set like before, only this time it's what? 4 numbers on the input side and 12 numbers on the output side. So it was a different, about 1 million lines long, and then tested the results. I'm not going to go through the same process again as before, just jump right to the result. Here is a result of the black line being the target. Now that target could be up and down from there, but it just happened to be this, and I picked these 2 thicknesses, 390 and 400. All of these are limited by what you've chosen for the training. This is N, this is K, and you can see across the K range a region where there's very close to why it's used for solar cells. It's very transparent. Below that wavelength or shorter, you see not such a good set of solutions, and that's a physics issue. And then at the longer wavelengths, we see a nice thing. And if you look carefully, you'll see that the black target line had some jiggles in it, and the doggone network followed the jiggles. How about that? I liked it. And of course, we want to go back again, the back way, and say, given that those were the answers, would we get this very not so smooth looking values of psi and delta as a function of of wavelength, and in fact we do, although not so well in the short wavelengths because we are having a physics problem there. So this we probably wouldn't bother making the measurements at that range if what you wanted was thickness. And not much more to say about that really. But you notice right away, I had to have 44 different networks to handle chromium on silicon. So if I wanted to put chromium on another material with K as 0, so I'm having to select K as 0 initially. So a transparent material, but that I didn't know in advance what was what was N at each wavelength, then I wouldn't have to train a separate network for every single thing. Cool. And that is doable. And the way I did that was to take the input neurons as 6. So there were 3 measurements this time at 3 different thicknesses. The number of neurons left it at 80. And now I've added the 2 parameters, the unknown real part of the substrate, and the additional thickness. So now I have 6 output neurons here. 6 and 6, that should work. Every kid knows that. And this is what we basically are looking at. I had in mind that this would be something that would be done during a deposition, and you could be gathering these numbers and comparing them and picking different sets of 3 and learning from doing that. I did not do that, but there's no reason you couldn't. And what do we get? Some arrows. Well, I've already mentioned those things. So we'll go back and look at, again, a test set of 500 tests, and at 409.2 nanometers. So we picked one of the wavelengths and went ahead and looked to see how well the predictions worked out for N and K and for N2 of the substrate. And it misses a little bit more of the substrate than but what matters to us is what the overall error statistic is. You can see the thicknesses are quite accurate. So there's more to be learned about this, but if I turn it around and look at the values of psi and delta that would be generated, you can see that a nice match there too. So looks like it works. And if we go for a target curve like we've done before, the black line again is a target. It could be up and down in that region over the range that was used for the training. Let me put myself back in so you know I didn't give up on you. And each of those red circles is a prediction. And you can see the predictions are pretty good. And we didn't have any idea what the substrate was for that. That's cool. And here's for K. Not bad. And don't forget, those can be improved by changing the network and changing the training. So we're not limited to what you see here. We're limited by what we do with the training process and the architecture. If you need more, you can train for it within reason, I'm sure. So here are the 3 thicknesses that were used for this particular experiment. Get myself out of the way. And you can see that they accurately predicted a thickness that was the same, practically the same at each wavelength. Good. And for 33 wavelengths. And this was the value of N, which was, I forget what material I used for this target. And that did a fair job of getting N. The substrate values are probably not the numbers we want to measure. We want to measure that. We just don't coat the substrate and measure it. So this would give us a more useful network because it could change the substrate and you could happily go, or you could go to a different wavelength. That's a whole other issue. And again, the psi and the targets came out nice, and it reproduced itself, and delta as well, in spite of the fact that the delta numbers were quite close. I thought that was interesting. So that's an unknown substrate example. And let's give it a hard go. Let's not use a nice smooth book value choice for N1. Let's take the N1 value and edit it by changing the 1, 2, 3, 4 values of N1 at those wavelengths. Interesting. Will the artificial neural network accurately land on the target? The answer is obviously yes, it did. So these these circles are not connected right and left to each other, other than through the physics of the whole problem. Interesting. We edited that, and it found the edited values, and at the same time got correct values for the unedited K1. Interesting. This requires a new way of thinking. A different way of thinking. Let's edit the thickness of D3, and sure enough, it follows it. You can see it has a little influence here. It doesn't surprise me, but pretty well follows, and that's a big edit there. Let's try some other edits. Here's the substrate edit. No problem. So this is a whole different way of thinking. Here's an edit for seeing the D3, and of course it affects this angle differently, I guess. Here's a whole bunch of different edits, and it doesn't care a bit. I thought you'd find that interesting. So what about chromium on unknown transparent substrates? And that's basically what we looked at, and I set it up, and I now have a way of doing this by just entering in the optical properties, and I've tested all these combinations with films of chromium, nickel, and BK7. You see 2 absorbing, 1 not absorbing. And substrates, you see a transparent, and then the semiconductor, and another transparent, and an absorbing. And these worked fine. Now, there's the empirical aspect to it, is that you might need to change the architecture a bit. But in each case, I used 1 million lines of training. I'd like to use 10 million, but the file size gets too big. And I won't tell you who, but it's been known to choke a very big machine with 10 million lines. So let's take another closer look at some other aspect of it, just for interest's sake. What about the value of n? What about the root mean square error of the 500 tests? And the answer is that it follows a sensible pattern. Now, this is for those who are concerned about continuity, and you can't prove continuity here because it would take infinite number of data points, but you can see that over 33 data points, there seems to be some continuity in the underlying process, and the K is also quite small errors, so I like that. And get me out of there. And the D is, I don't like the D that much because it's 1 nanometer root mean square error, but that's something that could be adjusted with training. So what conclusions have we able to draw here? And there's many other things that have been done, and other things that are in process, work in process here. So AI can replace numerical methods, maybe all of them, maybe not all of them. And a numerical method could be tagged on the end, by the way. Heavy computation is done offline. So you do that once. You post those files on Surface Science Spectra. Rick Hash already said he thought that was a cool idea. So we could have Urban's trained, and we could have somebody else's trained networks on there, and you could fiddle around picking what you want, download it. You don't have to do the training. They're already been trained. Once it's trained, it's trained. That's it. There are no local minima, so that problem goes away. There's no initial estimates. That problem goes away. And there's no stopping conditions. So these things that are a bit of a headache for numerical methods have gone. What do you get instead? Well, you get the problems associated with AI. Well, they're not too bad. It's fast. I put 100 times, but it's probably 1,000 times. And be up to, and it can be accurate, and the accuracy is adjustable by the user. So thank you very much. I hope that you got your neurons, your human neurons, stimulated by these artificial neurons. And I appreciate your attention. For that, I salute you.